Picture the scene. A cargo ship slowly approaches across the Caribbean Sea. From a distance, it looks like just another crossing. But ahead of it, there is no ordinary port. There is a hidden staircase of water in the middle of a continent. The image feels impossible. Cross from the Atlantic to the Pacific, that ship will not follow a flat trench. It will be lifted by water. Not by cables, not by cranes, not by engines pushing the hull upward. The ship enters a concrete chamber. The gates close. The water level begins to rise, and everything floating inside rises with it. The maritime giant is lifted as if it were resting on a liquid floor. Welcome to Invisible Structures. Today, you will understand the Panama Canal for what it really is, a structure that turns controlled water into lifting force. The question sounds simple, but behind it lies one of the most impressive hydraulic solutions in modern engineering. How does water lift gigantic ships? The answer lies in a system of locks, lakes, valves, and human decisions made with precision. The canal is about 82 kilometers long, but the secret is not only in its length, it is in its height. Along the way, ships have to climb roughly 26 meters to the level of Gatun Lake, cross an elevated route of fresh water, and then descend again to the other ocean. On a map, the canal looks like a line. On a map, the canal looks like a line. From the inside, it behaves like a machine built in stages. And that is what makes the scene so powerful. The ship arrives too heavy for any ordinary elevator, but engineering does not try to lift it by the hull. It changes the level of the world around it. Why does this climb exist? What prevented a straight passage between the seas? And how can a gate that seems motionless control so much moving mass? Before we enter this crossing, subscribe to Invisible Structures. Because today, the question is not just where the Panama Canal is. The question is how water can lift an entire ship. From a distance, Panama seems like a ready-made solution. A narrow strip of land separating two oceans. The most obvious idea would be to dig a sea-level passage, open one continuous cut, and let ships cross from one side to the other. But the terrain did not allow that kind of simplicity. Between the Caribbean and the Pacific, there was humid jungle, unpredictable rivers, fragile slopes, and a raised region at the center of the isthmus. Panama was not a flat board between two seas. It was a living landscape, with heavy rain, mud, rock, landslides, and disease turning every excavated meter into a fight. That is why comparing Panama with Suez helps reveal the problem. The Suez Canal in Egypt is closer to the idea of a great navigable cut at sea level. In Panama, taking that path would have meant tearing the central mountain range to an enormous depth and keeping the cut stable in one of the hardest regions for heavy excavation. History enters here not as a list of dates, but as proof of a physical limit. The French attempt in the late 19th century suffered from tropical diseases, rain, human losses, and the difficulty of removing earth on a colossal scale. The idea of a low, direct canal looked elegant on paper. In the Panamanian jungle, it became too heavy to carry out. The turning point came when engineering accepted a different logic. Instead of cutting everything down to sea level, it would be possible to carry the ships upward. Gatun Lake became the decisive piece. Created by damming the Chagres River, it transformed Panama's interior into a vast navigable surface. What had once been an obstacle became the route. The lake works like an elevated water highway, feeding the locks and allowing ships to cross part of the continent without digging one continuous trench from ocean to ocean. Think of a mountain road. Instead of tunneling through the entire base of the range, it climbs to a plateau, crosses over it, and descends on the other side. The Panama Canal does something similar, but with ships. The locks are the steps. Gatun Lake is the high stretch of the crossing. The water stored in the system becomes a tool. That decision also tamed the Chagres River, which could have become a flood threat. With dams and reservoirs, its force began serving the operation. The water that made the project difficult became part of it. Here is the second layer of the discovery. Ships climb because geography forced engineering to abandon the straight line. The canal did not conquer Panama by erasing the terrain. It conquered it by using the terrain to create an elevated passage. If this shift in perspective already makes sense, hit the like button now. It helps invisible structures show great structures in a more visual way, without turning engineering into a cold classroom lesson. Now we reach the main mechanism, the lock. A lock is a concrete chamber with gates at both ends. The ship enters slowly, guided by specialized pilots and assisted by tugboats or support locomotives, depending on the lock system. Once it is aligned, the gates close behind it. The vessel is isolated inside a box filled with water. And here is the most important detail. The water does not need to lift the ship the way a machine lifts a load. The ship is already floating. Even though it is gigantic, it is not resting on the floor of the lock. The hull displaces an enormous amount of water, and that water pushes the ship upward with enough force to support its weight. That is why it floats. So when the lock receives more water, the first thing to rise is not the ship. It is the water level inside the chamber. And because the ship is floating on that surface, it follows the rise. Engineering does not lift the hull. It lifts the liquid floor the ship is already resting on. From there, the principle is simple. A ship floats because water supports its weight. If the water level around it rises, the ship rises with it. The lock does not pull the vessel upward. It changes the height of the water where the vessel is already floating. To go up, valves release water from a higher level into the chamber. That water arrives through internal conduits, distributed to reduce dangerous currents. The level rises until it matches the next stage. Once the pressures are balanced, the front gate can open, and the ship advances into the next chamber. To go down, the logic reverses. Water leaves the chamber, the level drops, and the ship follows that descent while floating. Everything depends on control. Opening valves at the right moment, keeping the hull centered, avoiding sudden movements, and ensuring the gate only opens when the levels are safe. What is most impressive is that this process uses the height difference in the water as energy. Gravity creates the movement. Motors exist to operate valves, gates, and equipment, but not to lift the ship like a mechanical elevator. The original locks carry Panamax ships, vessels built to fit the maximum limit of those narrow chambers. Electric locomotives along the sides help keep them centered. In the expanded locks, inaugurated in 2016, Neo-Panamax ships use larger chambers, such as Agua Clara and Cocoli, with tugboat support and basins that reuse part of the water. This difference shows the evolution of the machine. The principle remained the same, but the scale changed. Ships grew larger, chambers expanded, controls became more sophisticated, and water had to be managed with even greater care. Inside the lock, everything seems slow because it has to be slow. A mistake in alignment can bring the hull close to a concrete wall. A poorly controlled current can push tons of steel in the wrong direction. A gate closed at the wrong time can disrupt the entire crossing sequence. That is why the scene is quiet, but tense. The ship barely notices the force moving it. From the deck, the chamber wall seems to change height. In reality, the level around it is being adjusted centimeter by centimeter. This is the heart of the project. Water lifts gigantic ships because the ship already floats. Engineering simply builds a room where that water can rise, fall, and obey. And tell me in the comments, what city and state are you watching from? Invisible Structures wants to know where the curiosity comes from among those who follow these structures from the inside. Now follow a real crossing. The ship arrives from the Atlantic side, coming in from the Caribbean, and enters the approach zone. Before it even reaches the first lock, it is already part of an operation involving schedules, authorization, queues, wind conditions, size, draft, and traffic direction. The canal looks like a road on a map, but it works like a sequence of controlled maneuvers. A Panama Canal pilot comes aboard to guide the navigation. He knows the curves, banks, currents, and risk points. The captain remains in command of the vessel, but inside the canal, local knowledge becomes essential. The first climb happens at the Gatun Locks, or, for larger ships, at the Agua Clara Locks. The cargo ship enters the chamber, is aligned, the gates close, and the water begins to do the work. In stages, the ship leaves the Caribbean level and reaches Gatun Lake, about 26 meters above the sea. When the final gate opens, the landscape changes. The ship is no longer facing concrete walls. It moves across an enormous artificial lake surrounded by forest. Gatun Lake is reservoir, route, and center of balance for the operation. Without it, the elevated crossing would not exist. On the lake, navigation still has to be precise. There are dredged channels, buoys, curves, crossing points, and depth limits. The water seems wide open, but the ship follows a defined route. Every movement has to consider other vessels, communication with control, and the schedule for the next stages. Then comes the Culebra Cut, also called the Gailar Cut. Here, the canal crosses the most symbolic part of the excavation. A corridor opened through Panama's rocky spine. The banks grow closer. The ship passes where there were once hills, mud, forest, and stone. The spectacle is not in the gates, but in the feeling of crossing an organized wound in the earth. This stretch reveals another risk. A problem there does not affect just one ship. It can stall the entire sequence. That is why speed, alignment, and distance between vessels are handled with care. The crossing usually takes 8 to 10 hours, and much of that time is coordination, waiting, and precision. As it approaches the Pacific, the ship begins to descend. On the original route, it passes through Pedro Miguel and Miraflores. On the expanded route, It goes through Kokoli. The process now reverses the climb. The chamber empties, the level drops, and the ship returns to sea level. In the end, the vessel that entered from the Caribbean appears on the other side of the continent. It did not cross a straight trench. It climbed liquid steps, sailed across an elevated artificial surface, crossed a cut through the mountain range, and descended again to the ocean. That is why the Panama Canal cannot be understood only as a shortcut. It is a continuous operation. While one ship climbs, another descends. While one crosses the lake, another waits for clearance. While tugboats correct angles, operators control valves, pilots adjust speed, and teams monitor water levels, weather, and traffic. The expansion of 2016 extended this logic to even larger ships. But even with newer, wider chambers, the essence remained the same. Enter, isolate, level, advance, cross, and descend. The result is a journey that seems calm on the surface, but inside depends on a rare choreography. One mistake can become a delay. One delay can become a line. And a line in a maritime corridor of this scale can become a problem for ports, cargo, and routes far beyond it. But there is a fragility even deeper than space, time, or ship size. It does not appear in the concrete wall or in the cargo ship's hull. It lies in the volume of water available to repeat this operation every day. After watching ships pass through, it is tempting to think the Panama Canal is a structure ruled by concrete. The gates seem like a permanent solution. The chambers seem too strong to fail. The cut through the land seems like a lasting scar. But the most sensitive part of the system is fresh water. Each lock operation moves enormous volumes between the lake, the chamber, and lower levels. Some of that water can be managed and reused, especially in the expanded locks, but the system still depends on reservoirs fed by rain. Gatun Lake is not just the backdrop of the crossing. It is the reserve that allows the canal to function. When there is enough water, the machine operates with more freedom. When lake levels fall, the canal has to adjust. Ships may face draft limits, the number of daily crossings may drop, lines may grow, and some cargo may begin considering longer routes. The fragility is not in a broken gate, but in one simple question: is there enough water up high to keep lifting ships? That question became more visible during periods of drought. The canal depends on rain, watersheds, reservoir conservation, and operational decisions. It also shares that water with human needs, because the region's lakes do not serve only ships. They are part of life in Panama. This is the final point of the journey. Engineering can cut through rock, build gigantic chambers, and guide vessels hundreds of meters long. But the force that lifts the ships still comes from something elemental: water stored in the right place, released at the right moment. At the beginning, we saw a ship arriving at the canal. Now we know what happens to it. First, it is captured by a chamber. Then it rises with the water level. It crosses Gatun Lake, passes through the Culebra Cut, descends through new locks, and reappears in another ocean. The Panama Canal is not just a passage between seas. It is a machine built to turn geography into motion. Across about 82 kilometers, it uses height, reservoirs, gates, and human control to make the impossible look routine. Changed your perception. The 26-meter climb, Gatun Lake, the Culebra Cut, or the dependence on fresh water that sustains this entire machine.